Dear jury members, BCAN colleagues, and friends, I hope you're all doing well. Today I'll be presenting my master's thesis, a re-examination of computational creativity through non-human animals. Before I dive in, I want to give a brief overview. The advancement of artificial intelligence suggests signs of computational creativity. However, the case for computational creativity is undermined by an anthropocentric bias. In this thesis, I attempt to broaden the theory of creativity in artificial intelligence by drawing observations from examples of non-human animal creativity. I also illustrate how this works in parallel with the 4E cognition theory. I conclude that addressing the underlying anthropocentric bias in evaluation of creativity in this way, 1, allows a stronger case for computational creativity, and 2, develops a more informed theory of creativity. The philosophy of artificial intelligence, or AI, has varied since the birth of the field. This is partly due to continuous developments in technology. Advancements in technology have both been the causal factors and the effects of these theoretical changes. This dynamic cause and effect cycle of practical implementation research and the philosophical theory underlying AI, which is also influenced by psychology and cognitive science, has made it difficult to establish a concrete definition of artificial intelligence. While in popular imagination, AI is usually thought of as talking robots, it can also be simulations, programs, and machines. In my thesis project, I look at all of these. I also specifically consider strong AI, a result of unsupervised programming where the responses of strong artificial intelligence agents to stimuli can be unpredictable. I take Margaret Boden's definition of artificial intelligence, which is comprehensive of the field. She says that AI is the development of computers whose observable performance has features which in humans we would attribute to mental processes. Even with a quick glance at the definition, the anthropocentric bias is quite clear. I modified the definition to be as follows: the development of computers whose observable performance or whose methods have features which in human and non-human agents we would attribute to mental processes. Margaret Boden also talks about the goal of artificial intelligence, which is to provide a systematic theory that can explain and replicate human cognition. Traditional philosophy of artificial intelligence tried to analyze whether this goal of artificial intelligence is possible and whether it is fruitful or fruitless. Yet the goal of AI implementation and the goal of philosophy of artificial intelligence created a kind of discrepancy, which I'll explain with an analogy. This analogy is called the bird analogy. Suppose one wants to create an exact model of a bird based on observable qualities, knowledge of the anatomy and physiology of birds, and other necessary data. However, in attempting to create an exact copy of a bird, it is highly likely that the bird will not be able to fly. On the other hand, if one wishes to model a feature exhibited by a bird, such as flight, it is possible to do so without having to create an exact model of the bird. In fact, the object that can fly will have differences in features and flight mechanisms than that of the bird, as it is in the case of an airplane. Similarly, the goals of artificial intelligence shape the practical implementation. The goal of trying to exactly replicate human cognition based on limited knowledge may undermine the process of implementing artificial cognition. Likewise, studying the human brain and attempting to replicate it may not necessarily result in the ability to create or understand cognition. Just as a bird and an airplane do not have the same mechanism in flying, artificial intelligence agents and humans will have different mechanisms and features in exhibiting features of cognition. Goals of artificial intelligence also led to branches in the field. The branch I will focus on in this presentation is connectionism, which gave rise to 4E cognition. One of the most popular connectionist systems is artificial neural networks. In programming a neural network, the programmer does not specify rules or input the model of the problem in the program. Rather, the network trains or learns how to give a solution. A shift in the view of the human mind from a Cartesian split mechanistic view, or Cartesian dualism, to the 4E cognition theory inspired connectionist AI. The main dispute in theories of cognition is shown in this diagram. How do cranial processes, extracranial processes, and extrabodily processes relate to one another, if they do at all? Dualism pertains that only cranial processes realize human cognition. 4E cognition holds a different stance. This is an overview overview of Fourier cognition, but I won't go into extraneous details, as even proponents of Fourier cognition dispute the details. The main stance is that cognition involves more than processes that occur in the brain. Extracranial and extrabodily processes have a role in cognition. Fourier cognition led to advancements in AI where flexible, adaptive, and unpredictable behavior could be seen in AI, which experts had not observed before. These advancements propose the possibility of the realization of other features of human cognition. Speculations on the possibility of artificial intelligence simulating human intelligence and perhaps even surpassing it re-emerged. They have been existent from the outset, however. The earliest debates on a machine's ability to think centered around the ideologies of Alan Turing. In his paper, Computing Machinery and Intelligence, Turing analyzes the question, can machines think? Here, Turing argues that the question on a machine's ability to think creates an intuitive response that leads philosophers to investigate definitions of terms, machine and think, but relying on highly debated definitions subverts the reliability of answers. He also notes that colloquial usages of the terms cloud judgment on the ability of machines to think. I agree with his motivation in constructing the imitation game. However, one of the major issues in the question that Turing does not directly address is the anthropocentric bias in the perception of thinking. Thinking is often restricted to thinking in humans, since it is the most familiar and accessible kind of thinking. Artificial intelligence, by nature of being artificial, will never be exactly like human intelligence. Yet the philosophy of artificial intelligence often stumbles into a pitfall of comparing and modeling artificial intelligence with human intelligence due to this preconception. In assessing the possibility of creativity in artificial intelligence, scholars encounter a similar challenge. Because of this, I will offer the shortcomings of the current theory of computational creativity by proposing the consideration of creativity in non-human animals in Chapter 3. But first, I will delve into the formal concept behind a general theory of creativity and computational creativity in this chapter. In this thesis, I focus specifically on Margaret BODEN'S theory of creativity for several reasons. She's a leading scholar in philosophy of creativity. Her theory is comprehensive of ideas in the philosophy of creativity, and her work on creativity in AI is particularly relevant to my thesis. A creative idea, according to Boden, is one that is novel, surprising, and valuable. To talk about what these terms mean, she introduces two categories and three techniques in creativity. The two categories are P creativity and H creativity. P creativity, where P stands for psychological, is the kind of creativity that is creative with respect to only the mind of the creative agent concerned. In other words, the idea is novel, valuable, and surprising when considering solely the context of the creative agent. It is personal creativity. Contrarily, H creativity, where H stands for historical, is the kind of creativity that is creative with respect to current knowledge of the entirety of history. Great works like Einstein's theory of relativity, Van Gogh's Starry Night, and Hayao Miyazaki's Spirited Away are examples of H creativity. The three techniques of creativity are combinatorial, exploratory, and transformational. Combinatorial creativity involves novel combinations of familiar ideas. Exploratory creativity involves exploring the potential of conceptual spaces, where Boden defines conceptual spaces as structured styles of thought. Culture and society form and shape conceptual spaces. And finally, transformational creativity involves making transformations that enable the generation of previously impossible ideas. Although she addresses novelty and surprise in these conceptualizations, she doesn't really address the term value. This is due to the elusive nature of the topic. She says, our aesthetic values are difficult to recognize, more difficult to put into words, and even more difficult to state really clearly. Moreover, values change, vary across culture, and are often disputed. Yet Boden does address the importance of positive evaluation of interest and the value of a creative idea. She states that evaluation is essential in determining what is creative, but also notes the difficulty in systematically explaining the criteria for evaluating an idea as creative, which poses a problem for creativity in artificial intelligence. In my thesis, I analyzed a recent example, computational creativity by the AI, the Painting Fool. The Painting Fool has three behavioral modes: skillful, appreciative, and imaginative. The Painting Fool employs a combinatorial technique in its skillful behavior mode, where it simulates the physical painting process. This flower montage is an example of a skillful behavior. It uses an exploratory technique by navigating the conceptual space of collage making, as is shown where it creates a collage on the Afghanistan war by reading an article by The Guardian. Finally, it uses the transformational technique, as in the example where it constructs a chair that does not exist in reality using generative techniques and 3D modeling tools. The Painting Fool states that its goal is to be taken seriously as a creative artist in its own right. This draws attention to one of the core preconceptions underlying creativity, the anthropocentric bias underlying our judgment of creativity. The judgment on AI producing creative work tends to be met with skepticism and even disregarded when consumers of the creative work discover that the work is by an artificial intelligence agent. Human intuition plays against the legitimacy of creativity in AI due to a biased belief that creativity is unique to the human species. This adds to the anthropocentric nature of the conceptualization of creativity. Thus, I argue that we must expand our view of creativity when assessing computational creativity by looking at the non-human agents familiar to humans, non-human animals. In this chapter, I draw observations from non-human animal creativity to shed light on computational creativity. To understand how BODEN'S theory of creativity and the terms novel, surprise, and value relate to non-human animal creativity, I examine the areas of non-human animal behavior where creativity arises. Non-human animals show creativity in tool usage, as in the example of the blonde capuchin monkeys that manipulate sticks to form screwdrivers in order to capture termites. Scholars observe creativity in non-human animals' search for resources, such as in the case of insects like butterflies that use chemical feedback from landing on a range of host plants to search for nectar. None are more famously genius in problem-solving as corvids. Carrion crows in Sendai City, Japan, drop difficult-to-open nuts on the road, effectively using automobiles as nutcrackers. Non-human animals use creativity in courtship as well. Male bowerbirds make unique, brightly colored, and artistic displays called bowers to attract female bowerbirds for mating. This behavior is also observed in male pufferfish, creating precise, artistic, geometric circles using their fins in the sand in courting females. Many examples of dolphin creativity are in dolphin play. A sea life park researcher trained dolphins to display creative tricks with their bodies. One of the many examples of octopus curiosity, researchers recorded octopuses using coconut shells as stilts for walking. If one is not convinced of non-human animal creativity through these examples, the argument of creativity being a necessary feature for evolution is another approach to arguing for creativity in non-human animals. Non-human animals can also be creative through training. Trainers at the Sea Life Zoo use reinforcement learning to enhance the creativity of dolphins. Insect resource searching shows that creative ideas can arise out of trial and error. Creativity in non-human animals is social in that a single non-human animal's creative idea can influence an entire community of the same species to adopt the idea. It is social in that non-human animals are creative in communication with each other and with other species. It is also social in interaction, whether it be interaction with the same species or with others. Robert Mitchell makes a comparison between creativity in human sports and creativity in dog-human social play. He quotes, "Creative acts such as deception in sports, as in non-human animal play, need not indicate that well-thought-out reason directs the action, but rather an unconscious realization of the possible movements of the adversary." In this chapter, I have argued that non-human animals are not only creative, but challenge the anthropocentric definition of creativity. This is especially necessary in the field of computational creativity, as artificial intelligence, though often modeled after humans, is after all still a non-human agent. Through the broadening of the scope of creativity to include non-human animals, the evaluation of computational creativity is more informed and less biased. In this chapter, I'll address anticipated counterarguments. Consider the four cases. My friend's 2-year-old son is bilingual in Turkish and English. Once when my friend asked him to come to the kitchen, he replied, "Come on, Maycem." He created this unique phrase by combining the Turkish suffix for "I will not" to the English phrase "come on." An orangutan used a similar method to describe watermelon when she was introduced to it for the first time and signed for candy fruit. The orangutan, like my friend's son, combined two words or parts of words in her already existing word database and created a new expression. Remarkably, Shakespeare used a similar method to create over 1,700 words in the English language. Shakespeare created many of those simply by conjoining two words or by adding suffixes and prefixes to words. Finally, the program JAPE creates punning riddles using combinatorial creativity in a similar way as my friend's son, the old orangutan, and Shakespeare. There are a few points to be made here. This would mark the creative act by Shakespeare as clearly creative, but would question whether the act is creative in other cases, especially in the case of the orangutan, the non-human animal, and and jape the program. Thus, most judgments on creativity by agents other than humans are negatively biased, and this must be taken into consideration when discussing creativity in non-human agents. Second, Shakespeare is given the label of a creative individual not only because of one or two instances of using combinatorial creativity to create words, but because he does this over 1,700 times. My friend's son, on the other hand, has exhibited far fewer instances of his creative ideas, and the orangutan even fewer than my friend's son. Nevertheless, one can still recognize these agents as creative in these specific instances. The point also stands in recognizing an agent as creative in one specific area rather than being creative in many areas. Third, the agents have specific goals that they were trying to achieve in the process of which creativity emerged. It is vital to note that not all these agents had goals to do with creativity. As in the case of non-human animals, the goal can be play, curiosity, sociality, or adaptation. The agents may not even be directly or consciously targeting their goals. The creative act can emerge in interaction or social circumstance, as was probable in the case of my friend's son and the orangutan. Finally, many can use Dreyfus's argument against Turing as a counterargument to my thesis. One can contend that artificial intelligence cannot be creative without an animate body form. At first glance, this seems to work well with the theory of mind and body posed by 4E cognition, which challenges my thesis even more, but this is a false parallel. The octopus is a perfect illustration of this point. The octopus's body is radically different from the human body, and yet it displays a sophisticated cognition. Moreover, an octopus's cognition is unique precisely because of the unique features of its body. The structure of its nervous system functions like a body-distributed brain, such that its arms make decisions, allowing it to react to its environment much more quickly than other species. The example contests the notion that cognition is restricted only to the human body. It does not necessarily assert that cognition is restricted to animate body forms. If the octopus gives a surprising understanding of the diversity of cognition and how that diversity is related to the form of the agent, it could be similarly surprising to widen the notion of cognition to other body forms. Instead of restricting creativity in artificial intelligence to be imagined through the human body, the unique distributed nervous system of the octopus can be taken as a guide in research in computational creativity. Regardless, researchers can bring about computational creativity through other unimagined body forms as well, which may lead to the emergence of unique creative methods or examples of creativity. Having addressed the major potential objections to my argument, I return to the overall contention of this thesis project. In the spirit of Turing's response to the question, can machines think? I pose the question, can AI be creative? In Chapter 2, I argued that scholars must address the anthropocentric bias underlying the current theory of creativity to give a reliable response to the question. Chapter 3 demonstrated that expanding philosophy on computational creativity to include non-human animal creativity subverts the anthropocentric bias, and Chapter 1 showed that 4E cognition fits with the observations made through research of non-human animal creativity. 4E cognition theory holds that features of cognition are not solely brain-driven activities, independent of the rest of the body or an agent's environment. They emerge in interaction with other facets of cognition, other agents, and the environment. Creativity, therefore, is not a brain-driven feature of cognition, as confirmed by examples in non-human animal creativity. Examples of creativity in non-human animals show that creativity can emerge through activities where the agent has purpose different than to be creative, such as tool usage, resource search, problem solving, curiosity, adaptation, mating, and play. They also show that creativity may emerge in social interaction, such as through communication or through the spreading of a creative idea in a population. Creativity may emerge in trial and error, or conversely, an agent can be trained through reinforcement learning to be creative. Additionally, creativity emerges as agents adapt to novel environments in evolution. All these observations of non-human animal creativity show the diverse manners through which creativity may emerge. These observations on creativity are not unique to non-human animals, as they are also relevant to creativity in humans and artificial intelligence. With these philosophical considerations in mind, I will conclude the re-examination of the issue of computational creativity. The case for the legitimacy of computational creativity is clear. It is not radical to state that AI can be creative. Many artificial intelligence agents, such as the painting fool, already are creative. The impulse to disregard computational creativity is driven by an anthropocentric bias. Moreover, creativity in non-human agents, such as non-human animals and artificial intelligence, elucidate many aspects of human creativity. They also challenge misconceptions in the theory of creativity. Creativity is not a uniquely human trait. It is also not the output of a only brain-driven process. Creativity is an emergent feature that surfaces in interaction with other facets of cognition, the environment, and other agents. Creativity is a feature shared with other non-human agents, including artificial intelligence. Thank you for your attention. The discussion will continue on Zoom. I really look forward to seeing you all. My references for the image sources used in the slides are here, and a full list of references used in my thesis project can be found in my thesis draft. Thank you again for your attention.